Today's stuff, 6.5. So 6.5 is solving linear inequalities. So this really takes and kind of combines two things that we've done before. Let me quick write this first. It combines one, earlier this year we graphed inequalities. We did either the solid boundary line or the dashed boundary line, then shaded one side of it. It kind of takes and combines that with eventually doing like two inequalities together. So you have this boundary line with a shaded region, this boundary line with a shaded region, where they're both shaded is going to be your final answer. But that's kind of what we're working towards. First thing, just want to do Roman numeral 1, identifying a solution. So identifying a solution. And it's kind of a no-brainer, but solutions are going to work in the inequality. So I'll write that down. You could probably skip it and be fine, but solutions will work. You could put them in the inequality and it'll be true. Work in the inequality. So example 1, I'm going to say is negative 2, 4. So is the point negative 2, comma 4 a solution to y is less than 2x plus 1. And what we're really working towards is eventually we're going to try to figure out is something a solution to like multiple inequalities. So for that, what we could do is we could just take and put the numbers in the variables. So my 4 goes in for the y, my negative 2 goes in for the x, and then you just check and see, is 4 really less than whatever you get when you do the rest of the problem. So I have a 4 is less than negative 4 plus 1. So 4 is less than, I start negative 4 on the number line, I go 1 to the right, so negative 3. So is 4 less than negative 3? No. So no, which tells us then negative 2, 4 is not a solution. So then a second example, and this one will work out nicely. So example 2, you could say is 3, 1. So is the point 3, 1 a solution to y is greater than x minus 4? So that same sort of thing, make sure you put the x and the y in the right spot. Sometimes people do the left one goes with the left one and so on. Instead we get 1 is greater than 3 minus 4. So 1 is greater than negative 1. And that's true. So then you know 3, 1 is a solution. So 3, 1 is a solution. How are we doing on those two? And that should be, we probably went through checking solutions before. At least we did the try the origin that tells you which side of the line to shade. That's kind of a repeat then a little bit. My plan was to do a graphing review. So if you remember this graphing totally well from chapter 3, skip it. But I'm just going to throw down a couple things that I thought people might make mistakes on. So graphing review. So kind of the inequalities. The first thing that messed people up sometimes is the boundary line. When did we have a solid boundary line? It's a solid boundary line with, is it greater than and less than, or greater than or equal to and less than or equal to? Gave me the solid. Yep. That if you have an inequality that's greater than or equal to or less than or equal to, you had a solid boundary line. Because that would be where it could be equal. So when we do the line is what actually graphing the equation with an equals in there, or graphing the inequality with an equals. So if you have a greater than or equal to, it could be equal, it could be the boundary line. Where if instead you had a greater than and or a less than, You have a less than, then it'd be a dashed boundary. Because those were the ones where the solution was everything right up to the line, but not including the line itself. The other thing would be when we did shading. I like picking the origin. So to figure out which side to shade, so put a point. Now I'm going to say usually 0, 0. So put a point, usually the origin, in the inequality. So first of all, it needs to be a point that's not on the line. So pick a point not on the line. So kind of my 3 little bullet points on here. The point can't be on the line. So you need to pick a point that's not on the line, which is why I put usually 0, 0. 0, 0 is just the easiest one to do. But then from there, if it fits, so if it fits, so if we do what we did in Roman numeral 1, put the point in the equation, or in the inequality comes out to be true. So if it comes out to be true, if it fits, shade that side. Or shade the side that has that point in it. If it doesn't fit, and by that I mean if we came up with an example like this where we had 4 is less than -3, if it's something that just comes out blatantly not true, shade the other side. So that's the real quick review on how to do the graphing. Does that make sense? And then the plan is we'll just do a couple of the graphs. So my Roman numeral 3 then is actually going to be graphing. The equations, or the inequalities rather, will be a little bit tougher this time around because we've done a couple more different line equations. So example 3, you could get a nice one like y is greater than 2x minus 3. So if we have y is greater than 2x minus 3, if I go with graph paper, what could you tell me about that line? We're better at graphing them now. We can do faster than what we did in chapter 3. What point do you know is on the line for sure? -3. So my y-intercept has to be -3 because this is in that form of y, hate to say equals, but equals mx plus b.
Always going to be in that form?
Not always. We'll do one in standard form next. But we know the y-intercept, the b, is going to be my -3, and my slope is 2. 2 or 2 over 1. So then from there we could go up 2 over 1, up 2 over 1, up 2 over 1. You could go down 2 and then left 1. But we're going to get some points like that. Now we need to determine solid boundary line, dash boundary line. Dash, because we have this greater than right there, it has to be dashed. So as I put my boundary line in, I try to make like a dash boundary line.
Wait, have we ever graphed them like that? I thought we used to put on a straight line and then do open or close.
We did that if we just had one variable. If there just was an x and you put it on a number line. We did these at the very end of chapter 3. So it's been a while.
Yeah.
Now from there we need to decide, do we shade up and left or do we shade down and right? So I'm going to pick that origin and see, well, does the origin work in my equation? So if I'm going to go over on the side a little bit, we had y is greater than 2x minus 3. The reason I like putting in the origin is it makes the math easier because 2 times 0 just drops out. So I have 0 is greater than -3. Is 0 bigger than -3? Yup. So then the origin works, so we shade to the left side of our dash boundary line. So another example, but this time we'll do standard form. And I'm going to actually write over here because I need the space. But if I do a 5x plus 2y is less than -8. This was the type of equation where I encourage you to find the x and y intercept. I think that's the easiest way to graph them. So first what we'll do is we'll put a 0 in for x. So if we're trying to find where does it cross the y-axis, put a 0 in there. So 5 times 0 is just 0, right? So this part just drops out. You could kind of pretend that's like a 0. So positive 2y is less than negative 8. I divide both sides by 2. Divide both sides by 2, and I come up with a negative 4 for my y-intercept. And then let me fix my equation. All right, or my inequality. Now I'm going to take and figure out the second one. I'm going to take my 0 that's now here in the y. I'm going to put it in for y. 2 times 0 just is 0. So it's like I have a 5x plus 0 is less than negative 8. So to find my x value, I divide both sides by the 5. And then that would give me x is a negative 1.6. And once we're there, we could graph our points. So I have over 0, down 4. And I have left 1.6, so somewhere right around in there, up 0. So I have those 2 points. Now, if I try to save my original equation, so I had a 5x plus 2y. Boundary line, solid or dashed? Dashed. I did dashed again because it's less than. If that had been less than or equal to, then we'd have to do solid, but it wasn't. So now I want to take and do a dashed boundary line. Be a little tough without a ruler on this thing, but
Wait, what would the slope be? 5 over 1?
slope is negative a over b for this kind. If you think back, slope was negative a over b. And this was in that form of ax plus by equals c. So we don't need the slope for this equation to do what we're doing. But if we wanted to get the slope, slope would be negative 5 over a positive 2. So negative 5 over 2. So if you wanted the slope, that's how you could get it. Now we want to find a point that's not on the line, so I'm going to go with 0, 0 again. And put that 0, 0 in my equation. And these are super nice because 5 times 0 is just 0. 2 times 0 is just 0. So that whole left side just becomes 0 every time for this type of equation. So we get a 0 is less than negative 8. True, false? False. 0 is not less than negative 8. So that the origin doesn't work, so we have to shade the side that doesn't have the origin. So a special type of story problem you'll get sometimes is going to be something like this. And I'll go back to my white paper. So I'm going to say example 5. I'll try to abbreviate it somewhat. But we have Ada's making jewelry. So Ada making Jethro. Jethro's not big into making jewelry. Is jewelry E-R-Y? R-Y? I don't know. I'm not a big fan of jewelry. Okay, so we have 285 beads total. And we're going to say necklaces need 40. Bracelets need 15. And we want to graph the possible combinations of necklaces and bracelets and so on that she could make. So we need to come up with an equation, or an inequality actually, I suppose, for this. What's the total combination she could make without running out of the beads? What do you think? Maybe a good place to start is our variables. We want our variables to be N and B. You could do X and Y if you wanted to, but then I'd make sure you somehow identify X as the number of necklaces and Y as the number of beads or something like that. All right. So we have 285, 40, and 15. Somebody turn it into an inequality. Well, do you agree 40 is paired with an N? If you make one necklace, how many beads does it take? 40. 2 necklaces? 80, which is 2 times 40. So you should be able to say 40 times N, right? I suppose we could do capital N, lowercase n, but 40 times N tells you the total number of beads just for N necklaces. 2 necklaces would be 80, 3 necklaces would be 120. Bracelets, it's 15 beads for each bracelet, so we'd have 15B, right? One bracelet would be 15 beads, 2 bracelets would be 30, and so on. If I take and add those two together, do you agree that gives me the total number of bracelets used? Or total number of beads used?
Yeah.
And the total number of beads needs to relate to 285 how? Yep, less than or equal to. Very nicely done. Because she can't use more than 285, she doesn't have that many beads.
Wait, how do you know you have to add?
I'd look at it this way. This is like the total beads. This is how my brain looks at it. Total beads. So if you want to figure out how do you get that total beads, this is just the total for the necklaces. So the total for the necklaces. This here's the total for the bracelets. So if you do the total for the necklaces plus the total for the bracelets, that could equal the total beads, but it's more just to say you have to be less than or equal to that.
Do we have to actually solve it?
Here's the point I really want to try to make. Maybe we should do the really fast version of solving it, is this here. If we were to go through and do this, let me just cheat and look at my notes. You could get the two intercepts, right? You could put a 0 in. You could go through with that equation, inequality, and put in a 0, find the y-intercept, put a 0 in for y, find the x-intercept, which ends up being the y-intercept is 19. You could make 19 bracelets and no necklaces. Or you could make 7.125 of the necklaces and no bracelets. So we have two things. One, this point's going to be 7.125. This point here is going to be 19. Solid boundary line or dashed boundary line?
Solid.
Solid?
Yeah, right?
How do you get 0
Is
and
that right?
19?
And I kind of gave it away a little bit by the graph that I drew. But if we go through, we're going to find out that we need to shade this side here. But does it make sense to shade all those numbers? I'm going to argue no, because that means our x values were the number of necklaces. That means that you could make a -1 necklace. It doesn't make any sense to have a -1 necklace. So really what your graphing should entail would be really just this part here, because you can't make a negative. And if you really wanted to be a stickler, you could say technically it's just a bunch of dots in there, that it has to be like you put a dot at 0 and 0, put a dot at 1 bracelet and 0 necklaces, put a dot at 1 bracelet and 1 necklace. But we're going to say she can make a partial, she could get like halfway through a necklace, but she at least can't do the negatives. So really we shouldn't have this part here, this part here. So be a little careful if they give you a story problem. Ask yourself, do negatives make sense? Could you have negatives in your answer? Ready to get the very last thing?
Yeah.
Okay. Then the very last thing in this section combines what we were doing in the last chapter with, well, how do you get the equation for the boundary line? So I'm going to say an inequality from a graph. So inequality from a graph. And the steps aren't insanely helpful because I don't really tell you how to do it, but that's in the notes from the last chapter. So first thing is find the equation. So look at the boundary line and come up with an equation from that. Typically if you have a graph, it's probably going to be easiest just to use y equals mx plus b, because you'll probably be able to see the y-intercept. If not, you could go back to the old, I wouldn't write this, but you could go back to the point slope theorem for the line or point slope form for the line. Or if you could find any one point on the line, put that in for x1, y1, and then find the slope. But typically y equals mx plus b is going to work. Once you find that equation, then you look at the boundary line and ask yourself, is it solid or dashed? Because if it's solid, then you know that it has to either be greater than or equal to or less than or equal to. If it's going to be dashed, then it's just going to be greater than or less than for your inequality sign. Finally, once you have that, you need to decide, well, I know if it's a dashed boundary line, it's greater than or less than. You have to figure out, well, which one is it? So to do that, I would say I'm going to write less than or greater than, like to pick that. So less than or greater than colon. I would pick a point in the shaded region. So pick a point in the shaded region. And use the sign that works. As far as a point in the shaded region, if you're in this form of y equals mx plus b up here, if you pick a point that's on the y-axis, it's going to be a whole lot easier, because then this is just going to drop out because your x is 0. And you just can take your y-intercept and put it there in for y. So we'll do that a second. I want to quick do one example probably, although maybe we'll make a comment on like special cases. So last example, example 6 for the notes. Let's say I'm just going to do a real fast graph here. And let's say we have something with a y-intercept of 2. And I'm going to make it a dashed boundary line. Y-intercept of 2, make my dot really big. And I want to shade left and up. From that, I'm going to also just kind of make the assumption that we could look at our graph paper, see how it's lined up, and recognize that the slope is positive 3 over 2. So slope 3 over 2. Doesn't matter. I think it'd be negative 2/3. But if the reason it doesn't matter is if we go with that form y equals mx plus b. Somebody tell me where to put some of my numbers in here.
2 would be your B.
Yep, 2 is going to be my b value, so I can put a positive 2 in there. And my 3/2 goes in for m. So I have 3/2. So y, and then we need to figure out greater than or less than still. 3/2 x plus 2. If it's a dash bound, so that was first step. First step was find the equation. So now is it solid or dashed? It's dashed, so we know it's going to be greater than or less than, not the or equal to. So we need to figure out greater than or less than. And then I would pick a point. So I may be just going to go with, do you agree, this point here, which is going to be 0, 3. 0, 3 is in that shaded region. So now if I put my 3 in for the y, if I put a 0 in for x, I really just end up with this plus 2. So I have a 3/2 times 0 plus 2. Well, that's just going to drop out. So I have a 3 and a 2. Is 3 greater than 2 or is 3 less than 2? Yep, 3 is greater than 2, which then means my inequality has to be a greater than, because we know that that 3 works. So y is greater than 3/2 x plus 2. And we didn't do the greater than or equal to because it's not a solid boundary line. Does that seem to go okay? The very, very last comment maybe would be to say, if you have a line that looks like this, so it could be a solid boundary line, could be a dashed boundary line, all horizontal lines, what's the equation or the inequality going to look like for a horizontal line? X equals something or y equals something? Horizontal line, what's the same? Are all the x values the same or all the y values the same? All the y values are the same? So it's going to be, I want to say y equals, but really it's going to be y is greater than something, y is less than something, but I'll just write the y equals. But it could be y is less than something, y is greater than something. If it had been a solid boundary line, y is less than or equal to something, or y is greater than or equal to something. If you have a vertical line, all the x values are the same, or all the y values? X. So it's going to be x is greater than something, x is less than something, x is greater than or equal to or less than or equal to. And that's all.